have here. All right, so when we stopped in chapter 8, we talked about electron configurations. So now the next step is what we call what the book calls the explanatory power of the quantum mechanical model, meaning armed with only knowing those electron configurations and what that means in terms of where electrons are, orbitals, that kind of stuff, can we actually use that to explain a bunch of physical phenomena and stuff that we actually see, can observe in real life? And the answer is, yeah, for the most part we can. So we're going to practice that now and look at some examples where that really works nicely. Okay, so first, ions. We've talked about ions. Chapter 3, we said, there's these ions that are common, that we don't have to use numbers for cations. And now we can kind of explain why that is. So let me get a picture here for you. So we've seen this kind of a figure before. But what's different now is we should be able to explain it. Right, so we saw something like this back in chapter 3, where we said, okay, group 1A make +1, group 2A make +2, aluminum and group 2A makes +3, and then we've got these -3, -2, -1. Like, you should know all that stuff from chapter 3. That's familiar. But now, why? What do we know now about electrons that allows us to explain those common things? Like, why do group 1A elements make +1 ions generally? What's going on with their electron configurations? All right, well, let's try it. Everybody pick a group 1A element and write its electron configuration. Pick a favorite. Start with a noble gas and write its electron configuration. Don't just stare at me, write it. Try it. If you need a suggestion, try potassium. And then try chlorine and chloride. All right, you got some configurations? So what do you see? If you look at the configuration of potassium, the atom versus potassium ion, and chlorine, the atom versus chloride ion, what's the difference? Or like, what kinds of things do you see in those electron configurations? Is there something similar between the configurations of the ions? Is everybody just tired? Let's talk about this. What's similar about the configurations of those two ions? Of potassium ion and chloride ion. Yes, they're the exact same, right? They're the exact same. They're both have noble gas configuration. So let's write those. So this is argon 4s1. This is argon. Chlorine, the atom, is 3s2, 3p5. And chloride, the ion, 3s2, 3p6, which is the argon configuration. Okay. So the two ions have the same configuration. And in fact, if you look at every ion listed in that table up there, those ions with predictable charges, what do you think is going to be true about all of them? Yeah, they all have noble gas configuration. So it's not like just some random collection of atoms that have predictable charges or ions that have predictable charges. It's ones where they gain or lose a certain number of electrons to achieve noble gas configuration, which calculations tell us is a particularly stable configuration. We also have evidence of this because the noble gases are the least reactive elements in the periodic table. So having that noble gas configuration is something special. And in this way, we can explain the observations of these ions, the fact that we observe these ions to exist with those particular charges. And the explanation for that is they have noble gas configuration. And so they're particularly stable. All right, so that's a way that these ideas of the quantum model of the atom end up explaining real physical properties. Okay. So another thing that we can explain in terms of electron configurations is what we call periodic trends. What happens to a particular property as we move from atom to atom across the periodic table or down the periodic table? And we can see patterns, we can observe patterns, and then we can try to explain those patterns by looking at the electronic structure of the molecule. All right, so we're going to look at basically 4 trends. Well, 5 trends. We'll see what we get to. But the first one we're going to look at is atomic size, and then we'll talk about how we explain that. The size of an atom is actually not a super obvious thing to define because of what we know about the structure of the electronic structure of atoms. So, what do you take as the atomic size? Is it the size of the nucleus? Is it the size of the outermost filled orbital? How do you determine that? And so there's different definitions of atomic radii or atomic radius. The definition we're going to use here is basically the average bonding radius. So like when this atom is bonded to another atom, if you kind of split that bond in half, how big is each one, sort of. And that's usually given in picometers. So you see that on the left there, radius in picometers. Okay, so this is a plot of atomic radius versus atomic number. So it's basically saying as you go up from 1 to 2 to 3 to 4 to 5 to 6, all the way up to, let's see, what's the biggest one up there? Maybe 57 or so. Here are the sizes of those atoms. So what are some trends that you can say, or that you can point to, based on those data? What are some things that you see happening, moving from one place to another on the periodic table? So they seem to kind of get larger and then smaller, and then larger and then back smaller.
If they're smaller, it's usually larger than the previous ones.
Yes, and the overall trend is larger, right, as we go from left to right. So where do you see those jumps happening? Why isn't it just going all bigger or all smaller? What's going on with the jumps?
Oh, So like when it equals out to like another element, like a different element.
Well, each dot is a different element.
Right.
So yeah, so like let's look at just the first one. So we go from hydrogen to helium at the very beginning, and then all of a sudden the size jumps way up to lithium. Then the size starts decreasing as we go to beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and then the size jumps up again with sodium. What's happening in each of those jumps?
We're going back to the first photo, which is S, and currently it's a sphere. It's like if we're measuring like the size of the where the electron reaches,
Yeah.
it gets like the biggest one reaches S, and then it comes together with the P orbitals.
That's not quite true, actually. The p orbitals tend to have more density further out than the s orbitals. But what you are seeing is, yes, it jumps up when you get to the next quantum level, the next s level. So the big jump between like helium and lithium is because we're going from 1s to 2s. And then there's another big jump going from the level 2 in neon, 2p, to 3s. So that principal quantum level, that n level, has a big effect on the size. So that's the first trend that I think we can point to here. Is that the increase in the n level increases the radius. So as we go from like lithium to sodium to potassium to rubidium to cesium, we see an increase in the radius, and that's going to be true for every comparable element moving down a group. You're jumping from level 1 to 2 to 3 to 4 to 5. You're seeing a big increase in the radius each time. So that's maybe the most obvious or most expected thing, that we know that the next n levels are farther away from the nucleus. They have a smaller pull because of the shielding, or a smaller attractive force because of the shielding, so we kind of expect, okay, it's going to get bigger and bigger and bigger. The other trend that we see is maybe a little more like counterintuitive. So what's the other trend going on? What happens as we move across the periodic table rather than down? The radius is decreasing mostly, right? And we'll talk about some of the exceptions, but it's mostly decreasing. So as we go from lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine to neon, we're basically decreasing the radius. And that's maybe less easy to explain at first because we're adding electrons. And not only we're adding electrons, but we're actually adding them to higher energy sublevels, from going from S to P, or S to P to D, or S to D to P. And even though we're adding these electrons to these, even though we're adding more and more electrons and adding them to higher energy sublevels, the radius is still decreasing. We're still getting this contraction. So how do you explain that? Ideas? Thoughts? Nothing. All right. Well, I'll give you the key, to this whole section. It's actually something we've already talked about. But let's take a look at the picture again. So at the beginning of this chapter, we talked a little bit about shielding, about the idea that inner core electrons shield the outer electrons from the nuclear charge. And so we have this thing called effective nuclear charge, which is the actual, or the nuclear charge that electron can be said to feel from the nucleus after the shielding is taken into effect. So if we're looking at a lithium atom, which we looked at before, lithium atom has 3 electrons. 2 of those are in the 1s and 1 in the 2s. The 1 in the 2s feels less charge, less pull from the nucleus, because those other electrons are kind of in the way, shielding it. Does that make sense? Because the negative charge is kind of like blocking it. So that shielding actually explains all these trends that we're going to look at today, from atomic size onto ionization energy and other stuff too. How can we think of shielding and effective nuclear charge? How can we use that to figure out what's going on with atomic radius? What does shielding and nuclear charge have to do with how big an atom gets? Well, let's take it step by step.
As they go across, like there's more protons in the nucleus, there's more traction.
Yeah, so as we go across, there's more electrons, but there's also more protons, right? If you go like 3, 4, 5, 6, 7, 8, those are more protons. All right, so is the effective nuclear charge on the valence electrons increasing? It is, right? Because all those new electrons, as we go across the row, are being added to the same n level. So the effective nuclear charge on an electron in the valence level of lithium is +1. What's the effective nuclear charge of a valence electron for beryllium? Maybe we can draw that next to it. So this one is lithium, right? For beryllium, we have basically the same picture, except the nucleus is now 4+. We still have 2 1s electrons. So we'll say, right, we still have 2 1s electrons that are shielding. The valence electrons, here's the 1s. There's 2 of them now instead of 1, but they're in the same shell, so they're not really shielding each other. So the effective nuclear charge for those valence electrons in beryllium is going to be higher. It's going to be +2 instead of +1. And as we move across that table, that shielding is going to, that effective nuclear charge is going to keep increasing as we add protons, because the electrons are adding basically to the same level. And so that nicely explains, for the most part, our trend here, that as we add these electrons and protons, we're getting a greater effective nuclear charge in the valence electrons, which is causing this pull and causing this contraction of the atom. Now, that also helps us explain the first trend, because when we jump to the next level now, all those electrons become shielding again, and now you've got this next level. So basically all of the atoms in group 1A, their valence electron has a +1 effective nuclear charge, because all those other electrons become core electrons, and now they're shielding. They're shielding those valence electrons. All right. So we can see some kind of weirdness happening here, some back and forth going on, and a lot of that has to do with the relative energies of the orbitals. So yes, in general, what we said is true, but like there's a contraction from the d electrons that then causes kind of a bump in size, because we know the p orbitals are actually a little bit bigger and a little bit shielded by the s electrons, kind of. So there's a little bit of weirdness going in, and then that tends to increase as you go down the periodic table. But the general trends that we see there, for one, you should be able to recognize those trends and know those trends. You should be able to judge atomic size. But also you should be able to explain it using those ideas of effective nuclear charge that we just talked about. All right. So let's try this. I'm going to give you some atoms, and I want you to arrange them in order of decreasing radius. So arrange them from largest to smallest. Okay, there's your 5. Try to arrange them from largest to smallest. And then compare your ordering with somebody close to you and see if you got the same ordering. If not, talk about where you disagreed. Yeah.
The last element is that SI?
Yes.
Okay.
Yes. So. Those orders look. We agree? Yeah. All right. So how are you doing this? How are you looking at those orders? Yeah. Okay. And so that's one trend. And what's the other trend? Yeah. So you're correct about the across the periodic table trend. What's the other trend that we see? Yes. The radius is, but the radii decrease as we go across, right? And where do they also decrease or increase?
They increase a
Increase going down. So there's two trends that actually sometimes can make it difficult to compare these radii. But in this case, these were chosen specifically because they do make sense to rank this way. So if we look at those on a periodic table, just kind of roughly place them various places. We know that, okay, so here's rubidium, here's calcium, sulfur, fluorine, oops, chlorine wasn't in there. And what else was it, silicon? So something like that. I know silicon and sulfur aren't right next to each other, but we just want general idea. So we know the biggest ones are going to be the lowest and ones down to the left. So the trend is basically going to go in order that way. So rubidium we know is going to be bigger than calcium. Calcium having those 4s electrons is going to be much bigger than anything that's just in the third shell. So that's going to be the next one. And then in terms of these, we know that silicon and sulfur are going to be bigger than fluorine, again, because they're in the next quantum level. And fluorine being all the way over to the right on the second row is going to be probably the smallest. So our order of decreasing radii would look something like this. Yeah? All right. So the trends are fairly easy to remember, and that's great. Make sure you can also explain them. Do you know what's going on kind of behind the scenes? Okay. A counterpart to the atomic radii are the ionic radii. So the radii of ions. Now if we're comparing similarly charged ions, the trends are the exact same. But if the charges are different, then things are going to be a little bit different. So what would you expect in terms of ions? Do you expect cations to be smaller than their neutral counterpart or larger? Cations are larger than the neutral ion? Okay, why?
More electrons.
Do cations have more electrons than their neutral counterpart?
Oh, wait.
The other way, right? Yeah. So cations lose electrons, so we're talking about positive ions. So we would expect those to be smaller, right? And in fact, they are. But what's interesting is they're much smaller than maybe predicted by what some of the things we've been talking about, and so we'll hopefully look at why that works in a second. So here's an example of some. We'll just grab a few of these. You can look at the rest in the book if you need to. Again, in picometers. So here's some atoms and their cations. You can see like the large gray shell is the atom, and the smaller red shell is the cation. So like lithium, 152 picometer radius, lithium plus 60. Beryllium 112, beryllium 2 plus 31. Boron 85, boron 3 plus 23. So it gets much, much, much smaller. And so why do you think that is? There's two separate effects that, they're kind of together. There's two effects that account for this big difference. What do you think one of them is? Let's take an example. Let's take sodium, for example. So sodium is 186, sodium plus 95. Two things that account for that big, big change in size. What's one of them?
For the sodium ion, like the 3s subshells we use, or no, for the normal sodium ion, or for the normal sodium atom.
Yep.
The 3s that we use for the Na plus ion.
Mm-hmm.
It's like removing a subshell.
Yeah, exactly. You're jumping down an entire, not a subshell, but an actual quantum level, an n level. So you're going from having an electron in n equals 3, a highly shielded electron in the n equals 3 shell. Then that's ionized, that's gone. So now you're looking at basically an argon, a neon atom, neon type configuration, that's going to be an entire shell smaller. But so here's the second part of that then. So the sodium ion, it says 95, right? If we flip back and look at comparison, so the neon atom, the neon radius is 70, and the sodium plus radius is 95. So that's actually a little bit counterintuitive now, right? Because you would expect that core is pulling it even more now that those things aren't as shielded. So that's interesting to think about that. I wonder if that's true for all of these. Well, okay, so we can see the opposite trend as we go across these. So sodium plus, magnesium 2 plus, and aluminum 3 plus are all isoelectronic. They all have the same electron configuration, which is the neon electron configuration. Everybody agree with me on that? All right. So why aren't they all the same size? If they all have the same electron configuration, why do the ionic radii go down? Going from what? There's more protons, right? So the higher the charge on the ion, the smaller it's going to get because you've got a greater effective nuclear charge pulling those electrons in. So the same number of electrons, but the effective nuclear charge is smaller, or I'm sorry, is greater, and so the radius ends up being smaller. So what do you expect to happen with anions? If the cations are becoming smaller when they lose their electrons, what do you expect anions to do? What? Yeah, they're going to get bigger. So as we're adding electrons to atoms, those electrons are going to have a kind of a decreased nuclear charge than what they're used to. And so you're going to end up getting larger ions there. And so you can see that here. That as the electrons, or as the atoms gain electrons, the anions end up being bigger. Right, so adding electrons without another proton means that you're going to have a larger atom, or a larger particle, larger ion. All right, so you feel good about size? Atomic size, ionic size, you can judge relative sizes, and so on. Okay. So the next trend we're going to look at is ionization energy. Ionization energy is the energy required to remove an electron from an atom in the gas state. So taking an electron from an atom. How much energy does it take to take the electron off the atom? The reason it's in the gas state, well, what do you think? Why do we measure things like quantities like this only from the gas state? Why does the atom have to be a gas in this case? What happens in condensed states? What happens in liquids and solids to atoms? Are they isolated atoms in that case? They're not. Right, they're connected to stuff around them, and that's going to affect their electronic behavior, especially in things like metals, where we know the electrons are kind of doing something a little bit different. So in the gas state, we're talking about a single solitary atom. How much energy does it take to take that electron off? Notice that these are all going to be positive numbers, the energy required. You have to put in energy to take off an electron. And that's even for the species that we think of as reactive. So something like a sodium atom that we say, oh, it really wants to lose its electron to get to noble gas configuration. Like, okay, compared to other things, yeah. But it still takes energy. We still have to put in energy to get that electron off of that sodium atom. All right, so let's look at those ionization energies and some of those trends. We're going to see, I'll show you a graph first, kind of like the atomic size, and then we'll look at some more specifics. So you can see from the graph here a similar trend to what we saw before. Or I guess we should say similar but opposite. So there's something going on as we go across the periodic table, and there's something going on as we go down the periodic table. So in general, what happens to the first ionization energies as you go across a period? They increase. Everybody see that? The lines go up as we go across a period. And then they kind of drop back down, go back up again. So that's telling us that it takes increasingly more energy to ionize an atom, to go from a neutral atom to a +1 ion, as we go across the periodic table. Okay, so just so we can get a little bit better sense of those numbers, let's look at another graph that shows us some more specifics here. So same thing, we're just looking at the numbers now. So you can see some atoms have much higher ionization energies than others, and the trend kind of goes to the right. So why do you think that is? Thinking about all the things we've been thinking about. Why does the we'll look at both trends. Why does the trend generally increase going from left to right in the periodic table? Why does it take successively more energy to ionize electrons from those atoms over on the right versus those atoms over on the left? Yeah, exactly. So I told you the effective nuclear charge is kind of the key to all this stuff. And so that's, again, the reason that we see this. As the effective nuclear charge increases, it requires more energy to tear those electrons away from that attractive force, from that positive negative attraction. So what we're saying then is, as we go to the right of the periodic table, the attraction between the nucleus and those valence electrons is stronger, and so it requires more energy to pull an electron away or off of that atom. So that's good for the general trend going left to right. What about the general trend going top to bottom? What do we see there? As you go down a column of the periodic table, what happens to the ionization energy? Decreases. Everybody see that? As you go from, let's say, whatever, pick a column, hydrogen, lithium, sodium, potassium, rubidium, cesium, the numbers go down. So what explains that? The orbitals, yes. How? What? You outsource the question? Yeah. Somebody help out. What's going on with the orbitals? It's very similar to what we said about the size, just the effect is the opposite. What's going on with the orbitals as we go down a column? Let's stick with the alpha metal. But
You're adding the whole other level.
You're adding a whole other level. And so with atomic size, we said that is increasing the size. So why would that be decreasing the ionization energy?
Because they're getting more shielded, so they're going to take less energy.
Sort of. Almost. They're the same amount of shielded, because as we add the protons, we also have the same number of electrons. But you're getting further away. So that attraction is getting smaller as the electrons get further away by being in bigger outer orbitals. Sorry, I'm tripping over my words a little bit this morning. Okay, so we got two general trends there, and we can explain them with these ideas of where the electrons are, what the electrons are doing. So now we're really going to test our knowledge of this stuff, and we're going to look at the exceptions. So if you notice, we said the general trend was as we go left to right, the ionization energy goes up. But if you actually look at, I think it's maybe clearer on this graph, and then we'll go back down to the numbers. There's actually a pretty regular pattern that kind of goes against the trend that we expect. So if we go from lithium to neon, yes, the overall trend is the ionization energies increase. But there's a little blip where it goes down right here, and there's another little blip where it goes down here. And that blip happens again in the next row. Blip, blip. And actually in the next row too, but there's d orbitals, so it gets a little obfuscated. So what are those blips? What's going on there? So if we say that, let's put it in real terms of some examples. So we say it is successively harder, takes more energy to remove an electron as we go from left to right. So as we go from lithium to beryllium, it takes more energy to remove the beryllium than the lithium because of the greater effective nuclear charge. But then what that's telling us is it actually takes less energy to remove that first electron from boron than beryllium. So what might you guess is causing that? So being paired or unpaired could be part of it. Yep, because we know that there's an energy cost associated with pairing an electron. So it might be a little easier to remove that beryllium electron than we thought. But that kind of goes against what we're seeing from the data. But hang on to that, because that'll come up in a second, in a little bit. So what might explain why it's easier to remove the single unpaired boron electron there? Where is that? Where is that electron? In boron. It's a 2p electron, right? So the 2s is filled, lithium, beryllium, and then we remove the 2p. So maybe that's it, right? And it is. The 2p orbitals, we know that the p subshell is slightly higher in energy than the s, which is why we always fill the s first before going up to the p. And so removing that p electron is going to be a little bit easier. So that's going to be our 2p1 electron, which is a little bit easier to remove. Okay, so now let's go to the next. So that's going to happen in each successive row. So that's why we see that same thing happening in sodium's row. That now we've got that flip on that aluminum for the same reason, because that's removing the 2p1. And I think you were right actually that part of that is also that having that full S shell, there is a stability associated with that, even though the electrons are paired. So that may be part of it as well. That one is a little higher than it should be, or than it would be expected to be. Okay, so let's look at the second flip. This one's maybe a little bit trickier. So we explained boron, and then we go from boron to carbon to nitrogen. Everything's going up as expected, and then all of a sudden oxygen jumps down again. Why is it easier to remove that first electron from oxygen than from nitrogen? Yes? Let's take a look at those electron configurations. So nitrogen's going to be 2s2, 2p3, and oxygen 2s2, 2p4. So what's so special about 2p3 versus 2p4 that could be causing this difference? Paired versus unpaired. So keep going.
So in 2p3, they all have, none of the electrons are paired.
Right.
And in 2p4, you have your first set of paired electrons.
Right. So in 2p3, we've got 3 unpaired electrons. In 2p4, we've got 1 pair of electrons. Okay, since there is an energy associated with pairing electrons, meaning it costs energy to pair those electrons up, that means that it's going to be a little bit easier to remove that paired electron than might otherwise be predicted. So that helps to explain what's going on between nitrogen and oxygen. All right. And that's also then echoed again in the next row, going from phosphorus to sulfur. You see another little blip. And in the row after that, going from arsenic to selenium. And then by the time you get down to the fifth row, fifth period, weirder stuff is happening, and it starts to get a little bit more obfuscated there. All right. Questions? Concerns so far? Everybody's good? Okay. Let's look at, so that's all first ionization energy. So this is all energy, the energy that it takes to remove 1 electron from that atom. Let's look at successive ionization energies. So that is what happens when we remove subsequent electrons. So we remove the first one, and then the second one, and then the third one, and the fourth one, whatever. And we call these ionization energy 1, ionization energy 2, etc. Ionization energy 3, and so on. So that's removing successive electrons from the same atom. What do you think happens? Do you think it takes more energy to remove successive electrons or less? No guesses? Yeah. Well, let's look at the numbers and see. So here's a table of successive ionization energies for third row, third period elements. Okay, so what do you see? Increases, yeah. Successive ionization energies are always going to be increasing. So it always, always, always takes more energy to remove successive electrons. Even in the cases of things where we say, oh, like calcium, what's in here? Not calcium, magnesium. So we usually say, oh, magnesium wants to be a +2 ion. We use phrasing like that, or it wants to lose its electrons to have a noble gas configuration. And that's fine as like a construct to think about it, but the actual energies tell us it doesn't really want to. It still costs an additional 1,450 kilojoules per mole to remove that second electron from magnesium. So, you know, in a reaction or something, that would be balanced by the electron, by the energy gain from something else getting that electron. But it still costs those energies. So the first ionization energy is the trends that we just talked about. That's just that first column. And then there's successive ionization energies. And one thing that you can see from the successive ionization energies, and I think there's some homework problems about this, is you can determine where in the periodic table an element should be based on its ionization energies. Because in between its valence and core electrons, you should see a major jump, like for aluminum, a major jump in the ionization energy. So the successive ionization energies increase as you remove 1, 2, 3 electrons. And then if you want to remove that fourth electron, the ionization energy goes up by a huge, huge factor. And that's because now you're removing a core electron. We know those are less shielded, they're more highly attracted to the nucleus, they're closer in. So removing the core electrons requires a whole lot more energy. And so that's what we see there. All right, and then the opposite of ionization energy is something called electron affinity. And this is the energy given off when an electron is added to an atom. So if we take a separate gaseous chlorine atom, we're not talking about chlorine gas, the chlorine molecule, just a chlorine atom, and we just add 1 electron, we should have a gaseous chloride ion. And the energy associated with that reaction is minus 349 kilojoules per mole. So if you add electrons to a mole of chlorine atoms and make a mole of chloride ions, then you would give off 349 kilojoules of energy. Okay, so that's called the electron affinity. Metals in general, most of the middle of the periodic table and most of the alkali metals, not all of them, but most of them, most of the alkaline earth metals have actually greater than 0 electron affinities, which means this reaction would cost energy rather than give off energy. And so we mostly only talk about electron affinity with the main group elements, the nonmetals over on the right. So that's why you see that in the book. All right, so there's a table of electron affinities, and you can see they're given as negative numbers because it's the energy given off when an electron is added. And we see kind of a little bit messier trends. There's not quite as clear of trends the way that there were with the ionization energies. For instance, if you look at the halogens, fluorine, chlorine, bromine, and iodine, it kind of goes right up and down. Chlorine has a little bit more of an electron affinity than would maybe be expected from the trend. And so there's all kinds of various things going on. One thing that we can use our skills that we already talked about to predict, if we look at the second row, you'll notice that nitrogen has a positive electron affinity, even though the general trend is for electron affinity to keep the magnitude of it to keep increasing going across the periodic table. So what's going on with nitrogen? I'll give you a hint. It's basically the same thing we already talked about. What are we talking about? Yeah, the electrons being paired. So nitrogen has 3 unpaired p electrons. If one more electron gets added to nitrogen, that electron has to get paired up into one of those orbitals. And so that ends up taking more energy than it would give off. And so that's why nitrogen has that positive electron affinity. And you see that same dip with phosphorus and with arsenic. So the fact that it keeps doing that is pretty good confirmation of that idea. And then the last trend we're going to look at is more qualitative than quantitative, and it's called metallic character. The degree to which an atom has metallic properties. So what are some metallic properties? What are properties of metals? What do metals do that non-metals don't do? Or what do metals not do that? Conducting electricity, so that's the big one. Metals conduct electricity. What else? They do have a high boiling point, but there are lots of other compounds and things that have high boiling points too. So I don't know if that's purely metal, because there's metals that have reasonably low boiling points. So like, yeah, I don't know that that's super unique to metals. Yeah. They tend to lose electrons. Yep. The materials themselves, so they conduct electricity. They also tend to be very good conductors of heat. So heat have very low specific heats or heat capacities, which means it doesn't take much energy to heat up a relatively large amount of metal. And so the degree to which atoms or elements act like metals tells you something about their metallic character. So if you were to guess, where on the periodic table would you say is the most metallic character? In the middle? Okay, good guess. We're in the transition metals. I will give you a hint. Because it's a periodic trend, that tells us that it actually goes one direction or the other, and not toward the middle. So if you had to pick a direction, what would you pick? Yeah, so we said before that blue staircase kind of separates the metals from the nonmetals. So in that case, which direction do you think would you go for the most metallic character? Yeah, the left side would probably be the most metallic elements, the ones that act most like metals. And then as we get closer to that staircase, we get a little bit less metallic character. So our general trends are to the left and then also down. So these elements down here are considered the most metallic in character. And that's kind of also goes along with the ionization energy and electron affinity trends, as you might expect, because the higher the electron affinity, the higher the ionization energy, the less metallic it is. Metal should be more easily ionized. So metallic character trends down into the left. All right. Questions, concerns so far? Is it okay? So that pretty much does it with chapter 8. As you go through the homework, you'll also see there's some examples of reactivity, of types of reactivity, types of reactions at the end of chapter 8. You can take a look at those. I don't think we need to really go through those formally. Whoops. But what I do want to look at before we go today is just the very beginning of chapter 9. Whoops, what did I do here? Oh, I went back to the beginning. So in most of chapter 9, what we're going to focus on is covalent bonding and how we draw these structures of molecules, how we deal with molecular structure. But the beginning of it, we're going to look at ions and ionic bonding. Now we know about ions, we've talked about ionization energy, we've talked about electron configuration, we've talked about structures of ions. But one thing we haven't really talked about is what happens when ions come together in a compound. So one thing is that we can talk about ions as just charges. So if they're charges, positive and negative charges, then what are they going to tend to do when they come together? If positive and negative attract each other, how are ions going to arrange themselves kind of in general? What would be the best way to minimize the energy or make it the most stable? If you have charged particles, what's the best way to put them together? What?
Put it with the uncharged.
Sorry, I didn't get it.
I feel like put them with the uncharged particles.
Okay, put them with uncharged particles? Maybe, but let's say we have an ionic compound, so we only have positive and negative. So let's say you've got some toys, and they're positively charged, half of them are positively charged, half of them are negatively charged. They're balls, let's say. How would you put them together to maximize the stability and the attraction?
Or negative and positive.
You pair up the negative and the positive, right? So you'd probably try to build a structure that packs them in as tightly as possible with alternating positive and negative charges. And that's basically what happens in ionic compounds. If you had some really, really big balls and some really little ones, that would change the packing, right? As opposed to if they were all about the same size. And that's pretty much what happens in a lot of our ionic compounds. We can think of them as basically the most efficient packing for the lowest potential energy of these charged particles. So if you imagine some configurations of charges like this, so this one is just electrons and protons. But if you imagine that as ions, clearly that middle one is the best, lowest potential energy, where you've got the maximum smallest distance between charges, and you've separated the positive ones from each other, so there's no repulsion by positive ones. So using alternate charges to separate things, and that's basically what happens in ionic compounds. So in something like sodium chloride, which does have a melting point. You can melt it. Although, oh, they don't have a picture here anymore. But as a compound comes together, I'll just use this one. If you could have sodium and chloride ions in the gas state, so totally separate, not interacting with each other, and then you put them together in an ionic compound like this, you're going to give off a lot of energy, right? Because the situation on the right is much lower in energy than the situation on the left. So if you had all these gaseous ions around separate, and then all of a sudden they get to interact with each other and attract each other, that gives off energy, and that energy is called the lattice energy. So the stability of an ionic compound can often be considered in terms of its what's called lattice energy. There's a couple different factors at play, but that's one of the reasons that we have our solubility rules. For ions where the lattice energy is very, very high, and the solvation energy, the energy of the water around them, is relatively lower, those are the ones that we call insoluble, because they would basically rather stay together than break apart and be surrounded by water molecules. All right, so there's a couple factors that affect lattice energy. Affected by two things. Ion charge is probably the biggest effect. So what do you think the effect is? Do you think ions with higher charges have greater lattice energy or smaller lattice energy? Greater, right? If things are more highly charged, then that energy released by them coming together and attracting each other is going to be relatively greater. So higher charges, higher ionic charges, is going to lead to higher lattice energy. And then the other effect on lattice energy is size. How do you think this affects it? Do you think bigger atoms have a greater lattice energy, or do you think smaller atoms have a greater lattice energy? Again, think about those toys. What's going to have the strongest attractions? Toys that little tiny things that attract each other, or big things that attract each other? So it maybe makes sense intuitively, but it's actually the opposite. And the reason for that is because of the distance of the interaction. So when you have large things, their relative space between the charges is much greater. When you have small things, the space between the charges is much smaller. So the toy thing is maybe not a great example in that case, because we think that a bigger toy is going to have a bigger charge. But let's say two things have the exact same charge. The bigger thing, that charge is more spread out, and the attraction is going to be lower. The smaller thing, the charge is more concentrated, the distance is smaller, the charge is going to be greater. So smaller ions lead to higher lattice energy. All right, and we can see some examples with that. So if we looked at just the series of alkali metal chlorides, lithium chloride, sodium chloride, potassium chloride, and then for whatever reason they skip rubidium chloride, maybe it's an outlier. It'd be interesting to see that. The lattice energies are This is in kilojoules per mole. Minus 834, minus 788, minus 701, and minus 657. So we can see the lattice energies, the magnitude of the lattice energies going down as the ions get bigger. And they show that pictorially in the book here. So you can see as the ions get bigger, there is more space relative between the charges, and so you have a less strong attraction. Okay. Something that we're not going to do, but I want to show you anyway. We're not going to do the calculations based on this, but you might do it next